Okay, so now everybody can see this, right? Stereochemistry, right? Okay. Okay, since most of the phytochemicals that we talk about in this class are organic compounds, just like I said earlier, so a lot of them are optical active. That means they have their absolute configuration. They are chiral. They have chirality. They are chiral organics. So, a major, like many of them, only a certain absolute configuration are bioactive. That means, for example, if a compound, its R configuration can be used to treat cancer, while the S configuration doesn't exhibit the cancer cell cytotoxicity. So in order to better understand this problem, first we need to talk about some basics about organic chemistry, that is stereochemistry or stereoisomerism. So as for isomerism, it is a major reason why there are thousands of different organic compounds, right? And there are three major types of isomerism: constitutional isomerism, geometrical, and optical isomerisms. And the latter two are stereoisomerisms. Let's first look at the constitutional isomers. So I have a question for you. If an organic compound have constitutional isomers, at least how many carbon atoms should it have? Any volunteers?
Come again?
I'm sorry, can you speak louder, please? It's difficult to hear you.
Can you please come again with your question?
If an organic compound have constitutional isomers, at least how many carbon atoms should it have? Do you know? Dr. Jia should have talked about this in your general chemistry last semester, right? In organic chemistry part. Did he?
So,
yes, we talk about this.
Yeah, so constitutional isomers, also known as the structural isomers, they have the same molecular formula, but differ in their sequence in which individual atoms are bonded. So that means if an organic compound have constitutional isomers, for example, if you have two carbon atoms, does it have a constitution isomer? No, right? If you have three carbon atoms, still no. However, if we have four carbon atoms now, the structure can be varied, right? We can detach the last carbon. For example, if we number from the left to right, this is the first carbon, this second, this is the third, and this is fourth. If we detach the fourth and reattach to the second carbon. That's a different structure, right? The one on the left, the carbon chain has 4 carbon atoms. So that's what is it called? What's it called? It's a butane, right? Butane have 4 carbon 4 carbon atoms, right? And its constitutional isomer on the right is 2-methylpropane or isopropane, right? The one on the left, on the right. So these two are constitutional isomers. So this is called a skeletal isomerism. In addition to that, we also have positional isomer. For example, this is the author nitrophenol. So on the benzene, there are 2 groups. The first one is hydroxyl, and another one is a nitro group, right? If the nitro groups and the nitro group and hydroxy are adjacent, this is called author position, right? So author means the hydroxyl and the nitro groups are adjacent, are close to each other, and the one on the right, we call this para-nitrophenol, because hydroxyl group and the nitro group are opposite to each other, right? So para position means the 2 groups are opposite. They're and we also have a meta nitrophenol. I didn't put in here. For meta nitrophenol, the hydroxyl group and the nitro groups, there is one interval in between, right? Between them. So that's called meta position. This is positional isomer because the groups are connect to carbon atom at different positions. The last one is the functional isomers. These are compounds of identical molecular formula, but which have different functional groups. For example, this is ethanol and this is ether. They have exactly the same molecular formula, but for ethanol, the functional group is what? Is hydroxyl, right? And for ether, the functional group is ether bond. So they are called functional isomers. We all understand that the different functional groups accounts for different property of organic compounds, right? And the major purpose of organic chemistry is to study the property of different functional groups, like how they react differently, therefore to synthesize various products accordingly. So ethanol and ether, because they have a different they have different functional groups, they act differently, right? Similarly, aldehyde and ketones are also functional isomers. They also react differently. For example, aldehyde has a reducing ability, while ketones doesn't doesn't have this reducing ability, right? So to conclude, there are 3 types of constitutional isomers. The first one is a skeletal isomer, and the second one is positional isomer, and the third one is functional isomer. This is for the constitutional isomerism. Another important type of isomer is the stereoisomers. For stereoisomers, they have the same atomic connectivity, but they differ in the spatial arrangement of the constituents atoms. For example, let's see. Okay, for example, this is 2 butene, right? This has a double bond at the second carbon with how many carbon atoms at the skeleton? It has 4, so it's 2 butene, right? And this is aniline. It's one of the simplest amino acid called aniline. These 2 compounds they all have their stereoisomers, but they also vary in the way the difference of the spatial arrangements. So basically, that means there are actually 2 types of stereoisomerisms also. The first one is enantiomers. The enantiomers are stereoisomerisms that are non-superimposable on their mirror image. For example, the aniline that we just talked about. So for aniline, the carbon atoms are linked with different groups. It is an amino acid. That means it has both amino and carboxylic group, and the carbon atom is linked with hydrogen atom and methyl groups. So the carbon is linked with 4 different groups. And because the carbon is a sp3 hybridization, the configuration of the molecule is tetrahedron, right? Now we imagine there is a mirror here, and this is so the one on the right is its mirror image to the one on the left, right? Now, no matter how you rotate this molecule, it can never be superimposable on their images. It's just like our left hand and the right hand cannot be superimposed ever, right? So they are called enantiomers. This is the molecule a model, and for this is a wedge perspective, right? The dash bonds are away from us, and the solid bonds are toward us. So this is an enantiomer. The second type of stereoisomerism is distereomers. Distereomers are stereoisomers that are not mirror image of each other. So they are stereoisomers that are not enantiomers. It's also called geometrical isomerism. This occurs when the carbon-carbon double bond are linked with different groups. For example, 2-butene. For 2-butene, when the mouse if we look at this carbon, it is connect with different groups, right? Hydrogen atom and the methyl group. For butene, the methyl groups, if the methyl groups linked with these two atoms at the of the double composing the double bond, if they are on the same side of the double bond, then it's called cis 2-butene, right? If they are on the opposite side of the double bond, then what is called, it's trans 2-butene, right? So there are two types of so there are two types of how they are how these groups are linked to the carbon atom at composing the double bond. However, if you take a close look at this, if the groups the carbon atom are linked with the same groups, then there are no stereomers, right? That means they are the same if you rotate them. So there are actually two types of stereoisomers, enantiomers and distereomers. For enantiomers, the molecules that can exist as enantiomers are said to be chiral. The chair means in Greek means hand, right? So a pair of enantiomers are just like our left hand and right hand and cannot be superimposed ever. So enantiomers are chiral molecules that are non-superimposable on their mirror images. And the chirality is a necessary and sufficient condition for the existence of enantiomers. The molecules are superimposed on their mirror image are said to be achiral. So they do not have chirality. Now, what do we call the carbon atom bonded to 4 different groups in enantiomer? We call it tetrahedral stereogenic center, right? And it's the chiral center, asymmetric center, or chirality center. It is denoted by a star. For example, this is carbon. Carbon is responsible for the odor of caraway seed oil. So it's a phytochemical, right? So for carbon, there is a chiral center here. This means this carbon is linked with 4 different groups. So the molecule has chirality, right? Also, for aniline, we just looked. We just look. We just took a look that for aniline, the chiral center is the carbon in the middle, the carbon atom in the middle, right? Because it's linked with 4 different groups. And for what is the stereogenic center? It is a center where swapping of groups lead to a stereoisomer. So for aniline, for the enantiomer, the stereogenic center is here in the carbon atom in the middle, and for geometrical isomer like distereoisomers, the stereogenic center is the carbon-carbon double bond here, right? How is stereochemistry? How is stereoisomers are found? So in the past, people found only one compound with the formula with this formula. It has only one carbon and 3 hydrogen X represents for any groups other than carbon or hydrogen atom. And they found also only one compound with this formula. However, people found 2 compounds with the formula carbon, hydrogen, XYZ. So people found that if the carbon atom are connected with 4 different groups, then there are 2 different compounds. They are a pair of enantiomer, actually. Like we just talked about before, in enantiomers, the carbon atom is linked with different groups. That's why they have chirality, right? These 2 are non-superimposable on their mirror images. The big sphere in this this is actually we can imagine as a molecule model, right? This sphere in the circle represents the carbon atom or the chiral center. When they are linked with A, B, C, D for different groups, then this is the chiral center. This molecule have chirality, and these are a pair of enantiomers, right? Okay. Now, a question for you. Are these enantiomers? Any volunteers? Okay, I see.
It looks, yeah, Lashe. On
Yeah,
the
I
picture
can hear
shown
you.
here, this is Christian.
Yeah, I can hear you, Christian.
This is Christian. Yeah. Actually, this looks like a mirror image, but just two of the elements on this carbon, like the B and A, is being shifted on the other side. So I think they are enantiomers from the picture view here.
Okay. Any different opinions? Anyone? Okay, so I see now it's time for to stop. So you can think about this afterwards, okay? And in our next class on Thursday, we will talk about this again, okay? All right.
Okay, Lashe.
I will post.
Okay.
Yeah, I'll post the the PowerPoint maybe in PDF file in the WeChat groups. Okay. Now it's
Lashe,
time.
thank you.
Okay. You're welcome. Now it's time. Okay. Goodbye.